Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you very much, and a very good day to everyone. Welcome to the AI for Good Machine and 5G Challenge webinar session. My name is Thomas Baskol from ITU, the International Telecommunication Union. The Machine and 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. And today I'm very excited to introduce our speaker and to host this webinar that is titled Driving Operational Efficiency in Mobile Networks Using Deep Traffic Analysis. This webinar discusses how NetAI leverages AI capabilities to forecast mobile network traffic with remarkable precision. And these predictions from the forecast are used to dynamically scale compute and capacity resources based on real-time need, aligning the vision of zero-touch networks or zero-touch network management. As always, we are counting on you, the participants, to create an engaging discussion. If you have questions, please type them in the chat or in the Q&A. And at the end of the session, we are going to have, we'll take the questions. And today's webinar is going to be given by Paul Patras, who is a co-founder and CEO of NetAI, as well as an associate professor in the School of Information, in the School of Informatics at the University of Edinburgh. Dr. Patras has over 10 years of experience in leading research at intersection of mobile network, artificial intelligence, security, and some of which has transformed from lab into commercial products. So I'm happy to welcome you, Paul. Thank you so much for making time from your busy schedule. I know running a startup and teaching in the university is quite time consuming, but you managed to make some time for us. So thank you so much and welcome. Good afternoon.
Hi, Thomas. Thanks very much for inviting me in the first place. And I'm sorry I wasn't able to attend the AI for Good Summit in Geneva last week. Yeah, it's a pleasure to speak about this. And this is some of the work I've been doing with my team at NetAI. I mean, as you know, we're a network analytics company. So we started this by we started some research in the lab, I would say maybe as far as 5 years back. And then some of that we realized had commercial value. So we decided to spin out NetAI and then embarked on this commercial journey. And then we realized there were a bunch of other new challenges that the industry was facing, and we had the right expertise both in AI and mobile networking. And actually, we learned how to kind of build neural networks that are specific to the mobile networking domain to tackle some of these problems. And then the question was, how do you close the loop? So how do you use the insights that you obtain from these neural networks in order to improve the operation of and the management of mobile networks? And that's what I'm going to talk about today. Before I begin, I'd also like to thank the participants for being here, and please feel free to ask questions in the chat or in the Q&A section, and at the end we'll have a conversation, and I'm happy to answer any of the questions you will have. I guess you're familiar with this type of scenario, right? You're trying to go and see some art gallery, or you go to a concert, and then lots of people are with their phones up and they're taking photos, and then those photos are being shared. And then despite, let's say, put aside the annoyance of the situation itself, for the network, this type of activity generates a lot of traffic. So you have mobile phones that are now pervasive, and everybody's using them for all sorts of things: social media, video streaming, mobile gaming, and so on. And as a result, as of 2023, we're witnessing more than 100 exabytes of traffic, mobile network traffic per month worldwide. That's a lot. I mean, pause there a little bit. So 100 exabytes, that's 10 to the power of 20 bytes. So obviously this poses quite some challenges to the mobile infrastructure that is the actual, last mile that has to serve the users. And if that wasn't enough, we're seeing increasingly more sort of applications that use devices that themselves communicate over a mobile connection without much human intervention. So you take, for instance, industrial automation, where you will have robots that are equipped with a host of sensors, and that those sensors will send telemetry to maybe some, central command and control point, and they'll get back some activation decisions, and that again generates a lot of traffic, aside from what we traditionally see just from mobile devices themselves. Or you have, new scenarios like autonomous transportation, where you have, let's say, fleets of cars or shuttles that move people from A to B, and these are, not manned, and they rely again on connectivity for the more sort of, computational intensive tasks that cannot really run on the device itself, on the car, on the bus just now, but instead they run in the cloud. So all that information has to be sent somewhere for processing, and then whatever commands that are relevant to a situation are going to be sent back. So then again, that generates further traffic. So you have volume, which is one thing, and secondly, you can already guess, there's a lot of diversity now. So it's not just like the use of mobile phone, but you have all these applications that have distinct performance requirements in terms of throughput, latency, reliability, and so on. So these are posing quite some challenges onto the mobile networks. So as a result, network operators are deploying, let's say, small cells, a mix of technologies, all sorts of functions, and that itself increases the complexity of the network and makes them really hard to manage. And despite the prevalence and the fact that we have been having networks for a while and we see an evolution, user experience is typically pretty bad. I mean, performance of these networks is not really kind of up to the mark needed to support those applications. And actually, if you take, for instance, 5G and so on, 5G has demonstrated poor return of investment, and that's in part, because operating costs, in a review conducted by TM Forum recently, it turns out that operators spend in excess of 65% of their revenues on operating costs. That has to do with engineering, energy, and so on. And then when it comes in terms of management, those decisions are based on information that is largely stale. You have some reports, and then you decide what to do for the next 24 hours with your network. And that, lacks that agility that those type of applications need. And then aside from that, you monitor performance using dashboards. You have, for instance, anomaly detection engines that use some thresholds. Then these are triggering some alarms. But in general, these are not sensitive enough, which leads to this problem of poor performance and poor user experience. So what you would need is to kind of anticipate how the network will behave and have insights in real time. So obviously, we're not the first people to think about this. I mean, forecasting has been kind of considered for a number of years now. The problem we're seeing is that, by and large, the models that are being deployed are quite rudimentary. They don't have, the best accuracy, if you want. And the big problem here is scalability. And what I mean by that is that, for instance, let's say you want to forecast what is the volume of traffic at the level of base stations. Yeah. So think now about the deployment, let's say the size of New Delhi, where you have tens of thousands of antennas. So if you take let's say an off-the-shelf model, the practice would be to basically train an individual model for every location. which is a gargantuan task. And then let's say you have a new type of application that kind of becomes popular. Think about TikTok a few years ago. So now the whole traffic sort of profiles change, and now you have to retrain all those models. So this is a process that doesn't really scale. But there are some transitions, and I think these transitions will actually make things a little bit better and simpler to manage. So one key element here is this idea of network virtualization. I think we've been speaking about this now for a decade, but we kind of start to see this, materialize. So the idea is that basically instead of using bespoke hardware that serves a single purpose, and that's a black box that is sold by a handful of big telco OEMs, now what you want to do is basically move those hardware functions into software that runs on general purpose compute. And basically you kind of virtualize them, yeah? So you run them on the same entity, and that can be on-prem or can be in the cloud. What this software is the ability to actually decide where to move, where to place those things. So you don't really need to have them at one physical location. You have, let's say, a pool of compute resources, and then you realize based on demand where to move those resources. And actually, if you had some knowledge, you know how many of these you need at any point in time. With that latter part, we're not there just yet, but to begin with, there are some advantages to this philosophy, because basically all of a sudden you have more flexibility in terms of how you manage your resources, and you're no longer tied to a single vendor or a handful of vendors. And the fact that you, for instance, think about using some cloud-based infrastructure that is maybe used by other players as well, you're also looking at not having to worry about maintaining that, but actually letting the hyperscaler do that for you, which in turn means a lower total cost of ownership. And this is kind of, to some extent, you have this flexibility, which ideally should underpin a set of new lucrative services such as industrial automation or autonomous transportation, which I mentioned in the opening. Now, what's the problem? I mean, we're not there just yet. I mean, to be able to kind of, manage and monetize all these resources, all these virtualized resources effectively, you need real-time and predictive knowledge of what the traffic demand is at any point in time, at any location in the network. So, of course, then AI kind of starts to make sense, because now you have a bunch of new tools, and GPUs are kind of accessible in terms of cost and so on. And you're trying to think like, hey, I can ingest a lot of telemetry and make sense of those demands in real time. And it's not really kind of, a nice to have. I mean, this is inevitable. This is something that it will happen, and it's already happening in some situations. And that's for a number of reasons. I mean, we started seeing already network functions being virtualized. I mean, AT&T claimed that they had 70% of their core virtualized by, I think, 2020. Then you have a bunch of new services that are being moved into the cloud, service platforms, customer support, all that kind of stuff. For instance, Vodafone moved some of that functionality in the cloud in Europe. And then you have other players who argue that they already have fully cloud native deployments. One example would be Rakuten, who had a cloud native Open RAN deployment in April 2020. I mean, mind you, take this with a pinch of salt, because ORAN is still being standardized. So we might not be just yet there, but we're certainly getting there, and I think there's no going back. I mean, because in essence, the whole idea is, people demand more and more traffic, and you have more applications and so on. So the question is, how do you meet that demand in a cost-effective way? You can't just like keep deploying resources and keep them on all the time. And that's something that will become apparent in some of the solutions that I'm going to present later in the talk. Okay, so what are the challenges then when you try to forecast things? So how do you go about anticipating network usage with high accuracy and in a cost-effective way? Well, it's not really kind of a trivial task. So take for instance, you have a city scale deployment and you want to understand how traffic will evolve over the next 2 hours. to drive those compute resources in an accurate and a scalable way. So you could, for instance, take an off-the-shelf LSTM, which is, I guess, to some extent industry standard. We've seen some of potential competitors of ours who deploy such models. Remember, one of the problems here is that you need to deploy this at the level of individual locations, yeah. And also, there are some spatial correlations. So LSTMs exploit some temporal correlations, but they don't exploit the spatial ones. And this is one thing that can lead to, a loss of accuracy. So what you're seeing in this plot, basically, I'm going to show, how LSTM fares with some of the things that we are doing. So on the x-axis, you have the number of parameters that you normally in log scale that you would normally have to train. And then performance loss means basically if you take out of these three solutions, the LSTM and NetSiebel and the Soothsayer, and I'm going to speak about each of them. If you take for every location the best performing one, and then you use that as the benchmark, you're looking at on average how much performance do you lose if you were using any of the other models. So if I take LSTM here, you already can see there is a performance loss, and there's quite a bit of variability in some performance, meaning that this model will work well at some location and questionably not so well in other locations. But if you go forward and then you think about the complexity scalability part, about which I kind of already alluded a few times, look at the number of parameters that you would basically need if you have a single model instead of a model for every antenna. You have a single model that you train at the level of an entire deployment. Yeah. So here, basically what we're doing, we're kind of taking as input to these models the signals of interest, say historic volume of traffic for every location, and that's what we feed into the neural models, and then we produce forecasts for each of these locations at the same time. Yeah. So you're reducing the number of parameters by or several orders of magnitude, which is quite significant if you're thinking about scalability, how much time it takes to train such a model, and so on. So in the rest of the talk, I'm going to speak about some of these models. So for Soothsayer, we use a so-called convolutional LSTM-based network, and then for NetSiebel, we're using some graph-based neural network, which is kind of a proprietary architecture. So I said we're going to do forecasting at city scale deployment. Okay, so the deployment typically looks as what you see here in the first box. So you have, you rarely deploy antennas on a grid, right? The antennas will be deployed based on, let's say the urban layout, population density, routes of transportation, and so on. So effectively, you end up with kind of a point cloud of sources of information, say volume of traffic. So if you want to use any sort of convolution type neural networks to ingest information from these sources, you can't really. You could just do a one-to-one mapping, but then the risk is that you're going to introduce some spatial distortions, which, remember, if we talked about, losing accuracy because you don't exploit spatial correlations, and these are quite unique to mobile traffic. So what you would like to do is, if you do a mapping to a grid, so you can process with convolutional type networks, you want to make sure that the displacement from the original location to that location on the grid is minimized. And there are a bunch of things that you can do here. In our case, we use a so-called Hungarian algorithm, which basically runs in polynomial time and has, I would say, introduces some, minimum location perturbation. So you don't really use significantly any correlations that you might have among, let's say, neighboring cells, from which maybe you will hand over a user when they move. So then what we do, so you have the input that is pre-formatted. So basically we use this so-called conv-LSTM sequence to sequence model. So idea here is kind of, you have a encoder decoder architecture. Yeah. So as an input, you take historical measurements. So this is traffic snapshot, if you want to think about this almost like images. So instead of having a pixel in an image, you have the intensity of traffic at a location that is of interest. So you take, let's say, 8, 12 snapshots like that, and then you also augment them with, let's say, some statistical features. Let's say, you know, what time of the day that we're looking at. Is there any sort of other statistics about the traffic around that point that I can feed? And then I actually give them to a sort of a fusion and embedding component, which actually then will provide input to these stacks of conval STMs. And then that kind of creates a sort of an abstract representations of those inputs, tries to mine some of the spatial and temporal correlations between them, and provides these to the decoder, which again has another stack of conval STM blocks. And those will effectively decode those abstract representations and then provide them to a set of embedding layers, which basically will give me, you know, the information that I expect. What's the volume of traffic I expect across the deployment over, let's say, K different time steps. So that could be, I mean, depending, and this is configurable depending, you know, let's say, what is your forecasting horizon? You want to do 4-step, 8-step prediction, so on. This also might depend on what is the granularity of your input. If your input is 15 minutes, for instance, granular, then, you know, you can think about 8-step predictions being like, you know, 4 hours, 2 hours worth of forecast, which probably is pretty good. So maybe before we move on, I thought maybe we spend a little bit of time to just explain a little bit what's the idea of these conval STMs. So this is how a conval STM cell looks like. Yeah. So the idea here is basically you have, it's kind of, this is a cell that kind of is somehow similar to LSTM, but it does replace these dense connections in the convolutional operations. And then it's been proven to work quite well in terms of modeling spatial temporal data. And there was a work actually dating back to 2016 when they started using this for predicting sort of what happens in video frames. And then we thought, hey, look, I mean, there's something actually we can borrow from here and adapt to the mobile networking domain, because now we can think about, you know, snapshots in a video as being similar to kind of a sequence of snapshots in the traffic demand in a deployment. Okay, so then what's the idea of like sequence to sequence learning? Yeah, so I mean, this is something that I guess probably it's, you know, again, it's not new, but now with the whole craze of generative AI, this is coming back. So this is something that people have been used in the past for kind of machine translation type tasks. Yeah, so you have a sequence of words and then you basically think about what you replied. So again, encoder, decoder architecture. So you have, in the traditional architecture, you have a recurrent neural network that encodes the input into some low dimensional representation, and then you have another recurrent neural network that will decode that into a sequence that's of interest. So probably think, I mean, if you're using, for instance, Gmail might give you suggestions, for instance, based on what you type, if you want to kind of complete the sentence in a certain way, right? So that's one example, which probably one type of technology which we're probably already using. So now we thought, okay, I mean, in the case of mobile traffic forecasting, what I would like to know is like, if I've seen some sequences of traffic measurements, I have some recent observations. I want to figure out what is kind of the most likelihood sequence of demands that I would see in, let's say, the immediate future, say 8 steps. Okay, so that's the philosophy here. And then I'm going to show some results, but I'm going to maybe take a step forward and talk a little bit about an alternative approach, which is something we're using now more recently. So here, remember, I did this kind of mapping from a cloud point to a grid because I wanted to be able to use convolution, right, on that input. And I did that in a way that kind of tries to minimize the displacement, but we were thinking like, well, what if we can actually, forget about that step altogether? Is there any other way in terms of like learning all these kind of geolocation representations without introducing any issues? So we said, okay, well, why don't we take that point cloud, draw some coverage area separation, so Voronoi type charts, and then build some graphs on top of them. And then we said, actually, we can also trim some of those graphs because they're probably too well connected. And for instance, one thing you could do is like, let's say you have two base stations that are kind of, adjacent. So theoretically, you could hand off users from one to the other, but they're actually too far apart. So the likelihood of actually that happening in practice is pretty small. So I can prune some of these edges, and then I have a kind of a more compressed neural network, graph representation of the deployment, and I'm going to try to do graph-based convolution on that. So again, I mean, if you look at this, it's very similar to what you've seen previously. The same philosophy. I'm taking historical observations of the traffic, and then I'm trying to produce things for the next period, which is of interest for me. So now if you look at the cells here, so you used to have conval STMs here. Now instead, we have graph convolutional operations, which basically learns directly on those graphs. And I don't need to do that pre-processing step, which is pretty beautiful. And also it entails fewer parameters that I need to train. And it works also better than the conval STM stuff. So, okay, you have the model, and then this question like, how do you train those models? Yeah. So one thing that we did was, typically people, train neural networks with, let's say, with MSC type loss functions or cross entropy or whatnot. But then we thought actually operators care more about two things. One is there is a cost of under provisioning. So if I don't have enough resources because I didn't forecast the demand in the right way, if this customer is, let's say, an enterprise customer, I'm going to pay penalties. And even if they're not an enterprise customer, I might not be able to provide them with enough capacity, which means I'm going to have unhappy customers, which are likely to churn. And likewise, if I throw too many resources at my network, so I over provision it, I'm just going to keep stuff running all the time, and that's going to, completely make my deployment inefficient from a cost perspective. So that's where basically, you get all this, big spend on OpEx. Just you have too many resources running all the time. So it's why don't we try to train those neural networks with a loss function that captures those two things? And this is what you're seeing in these plots. So the idea is that for the first segment, you have a flat penalty. Typically, it doesn't matter if you under provision by 1 megabyte or 2 megabytes or 100 megabytes. You have a service level agreement violation and has a fixed value, and that's a penalty for the operator. And you want to train the network not to underestimate demand. And this is what it does. And then the second part is basically the more resources I anticipate I need, the more I will have to spend, which again, it's not necessary. So ideally, I want to be in this kind of sweet spot here, where basically, I don't under provision and I don't over provision, or I just over provision by a little bit. There are some mathematical challenges as well here. I mean, if you would just take, if I go back, you look at this function, yeah. So it's not a straight line. Yeah. So if this was, a sudden change here, this would be a function that is not differentiable. So I wouldn't be able to use it for training. So introduce a tiny slope here, just to be able to kind of, train a model with that in a meaningful way. So what's the effect of using this? So this is what we call the operator monetary cost function, OMC. So how does it work with comparison if I trained it with mean squared error? So mean squared error is on the left here. So you see, if I train the network, I have a great architecture. It's going to do forecasting pretty well. And this is what you see with the dark lines here. But if I look down, like what are the errors? Again, like errors are pretty small, but what you see is that I very frequently have negative errors, meaning like I underestimate, not by much, but maybe that's enough just to kind of have introduce some penalties for me. So what we do when we train with the OMC is like, okay, I still forecast quite well, but if you look at the forecast now, it's kind of slightly riding that, ground truth, that service demand that I would actually know a posteriori. So I'm slightly overestimating. I'm still doing a decent prediction, but if I look at the bottom now at the error, it's like error is still small, but the number of, times that my error is negative is pretty small, which means it's unlikely for me to, to be in a position to pay any penalties if I was an operator. So that's one thing that we do, which I think is quite unique. And then the other thing is, I mean, if you go back here, you see you have all these variations, and these are notoriously hard to predict. So we thought, well, how can we sort of understand that to me, that's uncertainty, right? How can we capture that uncertainty? And instead of understanding, where I would expect the traffic to be, what if I provide some confidence band, which gives me some range of values where the traffic forecast will lie? So to do that, basically, we use this technique called Monte Carlo dropout. So the idea here is basically you randomly sort of deactivate some neurons, and then for every input that you take, you run it through this kind of ensemble models. Yeah, so you perform multiple inferences on the same input with different dropouts. And then basically this kind of approximates a Gaussian process. So basically what you end up with at the output is not a single value, but now you're kind of estimating the density of all the outputs. Yeah. So that will give you some information in terms of not a single forecast point, but a range of values where I would expect that forecast to lie. So how does that really look for an example? So this is something we did with a data set where we had information for a range of services. I'm showing just a sample here. So we took Vimeo, Spotify, some gaming applications, and Twitter. Dark line is ground truth, and then the predictions now are with light lines, with yellow if you're not colorblind. So what I'm highlighting here is areas where the model is kind of confident, meaning that those let's say confidence bands will be quite narrow. So there's not much variability, and it doesn't really matter knowing any range, because I'm pretty certain about what the output would look like. But there are other areas like here where there's a lot of variability. So here I want to be able to kind of give the operator this additional information in terms of where I expect the traffic to largely lie. I mean, again, you see, it's not perfect. You still have spikes which are notoriously hard to predict, but you're providing that additional information that allows you to kind of make some decisions in terms of like, hey, is this a service that I really monetize? Yes. Well, maybe then I will take the information at the top end of the band to allocate resources. Where if it's a service which really doesn't matter to me because nobody really pays to have high quality of service for it, say gaming, maybe it's an example right now, and that might change. Then I say, okay, I'm just gonna work with the lower end of that band and just provision resources accordingly. Okay, so we talked about two models that we use to do forecasting. So the question is like, how to use them in a real setting. So one thing we have been doing over the past months was to package these neural networks inside so-called XSubs. So this is a concept in the open radio access network philosophy. So if you're not familiar with that, this is kind of a new paradigm by which you're trying to kind of create a level playing field for multiple vendors to be able to work together easily, by means of open interfaces. You have open APIs that allows integration, and there's also, let's say, an ambition to kind of embed intelligence across the entire stack, network stack. So these XApps work with so-called near real-time run intelligent controllers. So controllers are, if you want, it's almost like an operating system that runs some apps. So in this case, the XApps. Okay, so this is where, let's say, I mean, microscope is some other technology we have, but we would have XApps here, and then basically what they do, they would subscribe, they will talk to a subscription management, and then they will output and input information from a so-called shared data layer. And then some of that information comes from this E2 node. So E2 node is like a generic name for anything really in the network. It can be a G node B, it can be a distributed unit, a centralized unit. So this is all kind of entities, part of this sort of disaggregated run access network. And then the flow here is really kind of, remember, we take aggregate traffic volumes for a period for every cell, and then we give them to the forecasting engine, and then the forecasting engine will produce some forecasts for those cells. And then in the case of resource autoscaling, we have a sort of a load balancing engine that basically translates these forecasting values into processing capacity that are needed at each centralized unit. So this is where some of the functionality has been disaggregated. And then we send those capacity updates back to E2 nodes, in this case, the CUs. And then basically, you're kind of reaching this point where basically you are understanding how to load balance, how to allocate processing capacity, which leads to, CapEx reduction, increased quality of experience for your user, and potentially some energy saving. Not clear exactly how that is quantifiable just yet at the level of a CU. Remember, here we had the simulator. We didn't have access to a full CU node, but we kind of build our own E2 node simulator because there are not that many vendors and integration is kind of hard. And as I said, ORAN is still being standardized. But I'll speak separately about energy. So how did we check if this actually works? So we had a data set from a real deployment. And then we said, okay, so imagine that the operator now kind of moves to ORAN and takes all these, it's all over 240 antennas that, let's say, are clustered and managed by a centralized unit. So CUUP means user plane. So the user plane gives you aggregate traffic at the level of these, let's say, clusters. And then you get those aggregate volumes into the XApp. You do the forecasting, you compute the relative capacity for each CUUP, and then you send that information back to those CU entities. So I'll show you a quick demo just to see how this would work. So this is basically how forecasting works at the level. We had three CUUPs here. Maybe I'll pause a little bit. So continuous line is the actual ground truth. So this is information that, in an ideal case you would have, but in practice you only have a posteriori. Forecast is what our model predicts, and then we have a naive forecast, which is an exponentially weighted moving average, which you see in many cases is completely off in terms of predicting that traffic demand. And you run this for a while, and then you can also see how this forecasts are being translated into capacity messages. So basically, how much capacity I need at the different CUPs. So here you see the IDs for each of them, and then there is this kind of abstract notion of capacity that has been specified by ETSI, and then vendors can choose to interpret that in a way that is specific to their equipment. And then this is another visualization where basically you see on the left the forecast, and then on the right you see how the capacity allocation looks like. So what you see with the dashed lines on the right is basically, if I had perfect knowledge, okay, let me just go back there and pause. So how much how much capacity would I allocate at different CUPs, and with the bar is the decision made by the XSUB. So the point here is that, you know, the XSUB is using those forecasts and makes those capacity predictions in a quite accurate way, I would say. Okay, so the last piece I want to talk about is another XSUB where, again, we're using the forecasting, but here we're using this with the goal of kind of improving the energy efficiency of a radio access network deployment. In particular, we're looking at using those forecasts to decide how many carriers we need at the level of an antenna, so that we switch some of them off, or like we switch a base station off altogether to save some of the energy. So logic is kind of similar. You take throughput measurements over a recent historical period, you do some forecasting, and then you translate those into the number of carriers that you would need, let's say, for the next 15 minutes based on those forecasts. And then you send that information back to the E2 node. Here now the E2 node would be G node B, and say, okay, switch off some carriers and so on. So what's the kind of outcome here? Yeah, so we basically we recently did some demonstration at the Oran Spring Plug Fest, which completed 2 weeks ago. So the idea there was basically we would take 8 steps of historical traffic, and then we would do predictions for the next step, and then we will calculate based on these predictions how many carriers I need based on the forecast throughput. Yeah, and then basically that's the information that is being received by the various E2 nodes in my deployment. And what you see on the right here is basically, okay, some snapshots on the performance. I mean, one important thing is here is that, okay, I mean, this works quite well. I mean, I have very high accuracy. Yeah, I have very low prediction error, and then I can use this actually to, you know, to reduce the number of carriers, which is what you see in this plot. So maybe fonts are a bit small, but basically in a legacy approach, you basically, you know, so the x-axis here is an index of the different cells. So this is a deployment with about 270 cells. So at every location, based on the maximum throughput, I know how many carriers I need if I had like an always on approach. If I had perfect knowledge of the demand, that's what you see at the bottom. So the kind of the green shaded stuff, this is, you know, how many of them you would need over a period of 24 hours. And then with the oranges, if you use our forecasting engine to drive the you know, the number of carriers that you would need to meet that demand, that's basically how many carriers you would have, which is kind of nice because basically, you know, you can already appreciate that. I mean, we're reducing the energy demand for basically by more than 50%. And there's another question here is basically, okay, I mean, in that experiment, we reduced by, on average, by 61%. And there's a question of like, okay, if you switch off a carrier, you also risk not meeting throughput demands. So the latest results we have is that actually we reduce energy a bit less by 50%, but then we have, you know, over 99% availability, meaning that the chances of actually under provisioning are really small. So you're still maintaining user quality of experience, because otherwise you could just basically say, hey, look, I look at some historical data, I know when there is low demand, I just switch off some of the infrastructure, which will save some energy for sure. But the question is that impacting user quality of experience? Certainly it will be. And that's something we wanted to avoid. And then I just close by just showing you another snapshot of like some of the, you know, we readapted that dashboard just to basically show that, okay, how you can visualize the decisions that are being made. So what you see at the top on the left is, you know, how much power you consume in a legacy deployment. Obviously, that's flat. And then if you're doing decision making based on forecasts, then you have the line in the middle, and then if you had ideal perfect information, you would be somewhere on the line or the bottom. So overall, I mean, you can see overall, you know, how much energy you would save over, let's say, a period of 2 hours. So this is something that we've deployed together with the run intelligent control that's being developed by VMware, and we're quite happy with that collaboration with them, because yeah, they have a solution which is quite robust. So that's all I had for today. Before I take any questions, I'd just like to acknowledge the work by the entire team that has been involved in this effort, and that includes Sam, Rokas, you, Alexi, and Marco, who is one of my co-founders. So with that, I'd like to thank you for your time and happy to answer questions.
Thanks a lot for this insightful presentation. And right now, I'd like to invite my colleague Vishnu to moderate the Q&A. So Vishnu, over to you.
Thanks, Thomas. And yeah, thanks a lot, Paul. I think this is a wonderful session, and it's a pity that you could not for the AI for Good workshop. Actually, we invited Paul. Paul is too busy, so obviously with the startups and so on. So we requested him to come here, and he's here, and that's a wonderful session that we had. I think you know, before we were chatting with Paul, and I have experience of discussing with Paul. I had the pleasure of discussing with him the early development in our ITU focus group as well. So yeah, I know the approach that he takes. That's in many cases he has been proven right. So yeah, that's wonderful. I think in terms of the approaches, Paul, I think let's say the ORAN decision that you showed, right? That's the most interesting part. Can I ask you, why did you look at ORAN type architecture? Obviously, the technical benefits are quite clear, but maybe it is clear. But can I ask you, what were your considerations when you were looking at an architecture to host the model? And did you look at any other alternatives? And what are your thoughts?
Mm-hmm. Yeah, so I guess there are multiple things there. So one, I guess there's a sort of a joint kind of technical and commercial angle to that. So if you remember at the beginning of the talk, I said at the moment, like the mobile network infrastructure is largely controlled by a handful of vendors. And I think ORAN tries, and that's to some extent, you know, creates problems for telcos, because it's hard for them to sort of, you know, switch from one vendor to the other or bring some new innovative solutions. But also it makes it very hard for, you know, small players like startups like us to be able to kind of, you know, play in that space. So I think ORAN is trying to create a sort of a level playing field where it's easy for, you know, vendors of different sizes to come and innovate together in a much more agile way. And then the fact that you have all these open interfaces, and there is a sort of a mission to embed intelligence, but we thought this is an opportunity. Now, there are also challenges, and we kind of talked a little bit about this before we started, but from, let's say, from a commercial standpoint, you know, ORAN is not mature yet. It's still being developed. There's a lot of work in that space. I mean, we have an observer seat, and we know there's a lot of activity. But it might take another 3 to 5 years until we see kind of, you know, full scale ORAN deployments. Or, you know, I mean, I remember there was a piece I read by Vodafone recently, and they said, you know, by 2030 we plan to have 30% of our infrastructure ORAN. Okay, that's great, but that's only 1/3, and 2030 is still a long way. Which again, maybe for big players is not a problem, but for smaller players like us, it can be a challenge, right? Because that means that, you know, your revenue projections are kind of very far down the line. So you need to find other use cases where you can use the technology much quicker. So for example, one thing we are doing at the moment is we're packaging some of these AI engines inside NWDAF or as standalone modules that could work, for instance, alongside an OSS or an orchestrator. But yeah, I mean, in general, if you want to do resource management, you would have to have some degree of software in your network. Otherwise, it might be, the number of levers you can pull is somewhat limited.
Interesting. Yeah, thank you very much. Yeah, that makes sense. And as we discussed, the MWC demos that you guys did, and you talked about this with the VMware collaboration, right? That's quite interesting as well. Can I ask you, Hassan is asking, can the slides presented by Paul can it be made available? Yes, we will make it available. We will work
I
with
think
Paul
the video is recorded, so you'll be
Sure.
able to see the deck there. Yeah.
Absolutely. Yeah, thank you very much. We will do that. Let me see. So there is so yeah, you talked about the levers pull. So in that sense, does ORAN give you the flexibility with the schema? Because when we looked at ORAN, the schema of data that it gives, as well as the control, for example, you are using capacity controls. So that kind of messaging to get the data in the schema that you like, in the granularity that you like, and the control that you want to provision or configure. Are you happy with it? And do you see challenges?
I mean, I think a lot of the stuff is still kind of being specified. I think the E2Node interface is quite specified now. So basically, you have a set of key performance indicators that you can ingest and, I guess produce. There's like a bunch of other telemetry you can produce with the XApps. So far, I mean, for what we were looking at, things are pretty okay. The second question is about granularity, and I think that is on the one hand, it's use case specific. So, in theory, our models can make inference, at city scale within less than a second. So they're pretty fast. And then you can argue that, okay, look, I mean, then we can feed information about traffic demand every 100 milliseconds. And then we said, okay, man, it's fine, but then that signal would be very noisy. So whether actually making any predictions on that fine granularity makes sense, it's a big question mark. Because yeah, it's just, you end up having so much uncertainty, there's not really much to predict. Whereas if you aggregate in the temporal domain, things a little bit, then the signals become a bit smoother and it's easier to predict on them. Still it's not straightforward, because otherwise we wouldn't be doing what we are doing. But if there's too much noise, there's really nothing to be seen. So yeah, and I think this will also depend on the various vendors. So as I said, we built our own E2Node simulator. There are a bunch of vendors now that developed CUs, DUs. So there are some constraints in terms of programmability and so on that will give you different reporting granularity, but that's nothing that we can control per se. There will be a question at some point, if you have loads of information, what do you do with it? That's probably, you can think about, distributing things a little bit. One thing, for instance, I didn't talk about here is even like how do you train those models. So one thing we are doing just to make sure that we don't spend a week training a model, we have a strategy of doing distributed training. So we basically use multiple GPUs at the same time to accelerate training and basically complete a training session much quicker. And you can think about similar stuff in terms of a deployment. You have a very large deployment, it might make sense to break it up and then just forecast for a subset of that deployment and then have multiple instances if it's, let's say, national scale.
That is actually valuable insight. Thank you so much. In fact, that clarified many of our questions. Yeah, thank you so much. In terms of use cases, so you did mention use cases. So in terms of that, from what we could see from what you talked today, there are mainly looks like CUUP, capacity optimization. You will probably get power savings from it, scaling optimizations from it, and the carrier allocation use case that you mentioned. That is another part. Carrier usage optimization we can gain. So, are you happy with these two use cases? First of all, the benefits. Do they kind of outweigh the troubles, or you would like to see more use cases?
I mean, to be honest, so this last one I presented, and this is kind of fresh now. I think this is super powerful because if you look at it, 80% of the energy in a network is consumed by the run. So if you can cut that energy expenditure by half without harming user performance, that's massive. I mean, that reduces operational cost in a really significant way. There will be a question of like, okay, how can we deploy that today? Do we have the knobs today in the network to have that level of control? And if we do, what's the granularity of that? For that, we will need to do a pilot with the operator to understand, what's the art of possible. But I think it's a super exciting use case. I mean, everybody's talking about this, not just, I mean, we have we are living an environment crisis, right? That's no doubt anymore. But also like the cost of energy is through the roof. So everybody would be looking to reduce that spend. So.
Thank you. Yeah. I think you answered already my next question, which is, do you have enough levers to pull? Yeah. Thank you. I think in terms of just maybe a naive question, because we look at it in terms of models which sit somewhere, but you have seen them working along with your trials, so and the real data. So I want to ask you this question: which is worse actually, under provisioning or over provisioning, or there are different weightages to it? What is your opinion?
Well, I guess depends on how you look at worse from what standpoint. So if you're looking at it from an end user standpoint, over provisioning is not a problem. I'm just have more resources if I need more bandwidth, no problem. From an operator's perspective, I think both of them have a cost. So I think over provisioning has been the status quo, and I think this is what leads to this, poor return of investment. But likewise, under provisioning can have significant consequences in terms of, revenue flattening. So I don't want to name any names here, but if you can look at financial statements for the big carriers, and you can see for a number of them, the revenue has been flat for the past 7 years. And that's in part, and some of them also report year-to-year customer churn. For some of them, customer churn year-to-year is above 10%, which I believe is pretty huge. You'll get new people coming in, but if you're losing 10% of your customer base every year, existing customer base, that's it's not good. So I think both are bad. You want to be in that sweet spot, just don't over provision too much, but don't make your customers unhappy.
Thank you so much. And you talked about inference speed, inference latency. So the sweet spot that you're talking about, are you able to hit that at the right time with the right inference latency? You see that happening?
Yeah, so at the moment we don't have any problems with inference. As I said, we can make inferences at the deployment of, let's say, over 700 cells within less than a second. But reporting granularity is 5 minutes at best. So we have ample time to make those inferences. So we haven't yet met a scenario where actually, we need to make a decision, within less than a second. It might come, maybe if you think about scheduling, and then, the fact that you have to do maybe decision making at the level of, 1 to 10 milliseconds, that's a different perspective altogether. And in that case, a lot of stuff would basically probably be in hardware, and whether or not you need AI at the level of such fine decision making, it's a big question mark.
Cool. Yeah, thank you so much. I think we are running out of. There is Thomas. That's my cue to stop. Thanks, Paul. Thanks for coming and patiently answering all the questions.
Sure.
I know you are very busy, but you're here, and we could not get you to the summit and the workshop, but thanks for coming. Back to you, Thomas.
My pleasure.
Thanks a lot, Vishnu, for moderating the Q&A. I think it was very nice discussion, and Paul, thank you so much for the insights. It's really nice to see that you are really going into the field, deploying something that was started from the lab. We have been hosting the challenges for 3 years now, and there is quite interesting insights. And I hope you can, maybe one time in future, you can take a look on what has been happening. And yeah, we would love to have your advice or insights or contribution to the challenge as well.
Sure. Thanks for keeping me in the loop.
Thanks. So at this point in time, I'd like to thank Paul and everyone who joined the webinar. Thank you so much for joining and for sparing your valuable time. And announcements to all participants. Please note that the challenge is open for registration. We have a few problem statements that are open, and participants, some teams have been created. People are already competing, and we would love to have you all participate in the challenge. And also we have another session on Monday, a webinar. Please join us, and you can check the program under the AI for Good program page for details. And we are looking forward to your participation in the challenge and in our webinars. So from me and my colleagues at the ITA and Machine Learning 5G, I wish you a very good day. Bye to all. Thank you.
Bye for now. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool. This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.